Hey everybody. I hope that you're all safe and healthy. Um, I usually do some good news, bad news kind of a thing, but we're sort of all living through the bad news right now, so I'm going to skip that. Um, I know that some of you have lost jobs and that your parents are struggling, and I hope that no one in your family or your extended family is sick. Uh, And I also know that finishing the stats course is probably very low on your priority list, but you signed up to take the course, and so we're going to try to get you through it. As far as I'm concerned, you will get credit for this course, as much power as I have to make sure that that happens, regardless of how this all transpires. Um, so we're gonna try to get through the material. This course, of all courses that I teach, is one of the courses that psych majors will need to get to the next course, research methods. So, um, and also in the fall, if people feel as though they need more, uh, some review or whatever, I will certainly do that in the evenings and help people out. Also, before I forget, um, email me through regular email channels if you have questions. I'm not going to do a discussion thread or anything like that on Engage. If you have questions, as specific as possible, just email me. I'll be looking at email multiple times every day so I can help you. So other good news, in addition to getting credit for taking the course, the remaining two exams I'll be sending to you, so they will basically be open book exams. I'm not interested in tricking you. I'm not interested in making it any harder than it is. So you can use your textbook. You'll be able to view these videos as many times as you'd like, and then also uh, email me questions if you have them. So let's I was just looking at my notes, which I usually don't have, but I wanted to get that all out there. I really care for you guys, and I want you to, especially at this point in time, get what you need to get, the support you need to get, and get you through the course. So let's try to do this. We're going to get to the finish line. It's only, several weeks, I suppose, 6 weeks total. So I'm going to make a series of these videos, 15 I think, and they will be available to you through a link on Engage. You obviously know that because you got to this video. And I'm putting this up on YouTube. I think that's most accessible for people. Okay, so let's go. If you have any questions, write me email. I suppose maybe this first time around, even though there's lots of you, because I'm doing this for all three sections, let me know if you were able to access and watch this video. Shoot me a quick email and just saying, hey, I saw the video. I was able to see it. And let me know if there's any problems. Okay. Are we ready? Let's do our first session. Okay. So we've been doing most of the work we've been doing so far in this semester is descriptive statistics, like I had said before. Measures of central tendency, measures of variability, and then we got into z-scores, which standardizes our normal curve and allows us to use that z-score table when we need to get percentiles and so on and so forth. On Wednesday, before we left, we talked about how statisticians define weird, and that is as something in the extremes that's improbable, that doesn't happen very often, given the population parameters, and that is the mean and the standard deviation. Those are our gold standards. You already know that. And so what I want to do is really now push the envelope a little bit to talk about inferential statistics. And that is making inferences when we have incomplete data. That is, when we don't have the entire population, we're going to use samples to make guesses about a population. But I want to show you how this works a little bit. Unfortunately, and it usually happens right after spring break, this is, I think, the most complicated concept of the entire semester. But let's see if we can get through it. And I'm not going to go as deep as I usually go, but we need to just pick up one kind of concept to go further. Okay. So what do I mean by inferential statistics? So far, we've been working with data sets where we have all of the numbers or all of the data points that we're interested in. We don't need to make any guesses. We just need to describe what we have. For inferential statistics, what I'm trying to do is I'm trying to make a guess about what the population looks like based on some subset of the population called a sample. So if I have 2,000 people and I want to know their average age, if I don't have every single person, I can't calculate the average, okay? And inferential statistics allows us to use some subset of that population. So let's say that out of the 2,000 people that I'm interested in, I'm able to look at 100 of them. So what inferential statistics will do is it'll tell me, how likely is it that I'm going to be able to guess at the mean using 100 people out of the entire 2,000. And so that's really what I'm talking about. This is what political pollsters do all the time. So you might read in news or see on CNN that so-and-so has a 52% approval rating. Okay, the president has a 52% approval rating. Nobody asked me, right? And they probably didn't ask you either. And some people are like, well, how do they know it's 52% approval? Well, what they do is they use a sample, hopefully a representative sample, of the entire United States. Remember, there's how many people in the United States? Anybody? It's about 325 million. And of course, if we think about voting age, what would that be? Let's say 2/3 of that. So 200 million people. That's just as a rough estimate. And so these political pollsters, they certainly cannot ask 200 million people. And so what they do is they make phone calls and they try to ask people in urban areas, people in rural areas. They ask males, they ask females, different age groups. They were asking people in California, they ask people in Louisiana, they ask people in Maine, they ask people in Texas, the whole thing. They might ask 1,500 people. That's an extremely small percentage of 200 million. But if they do the sampling in a way that it represents the larger population, then they can get a good guess at what the population mean is, and in this case, what is the average approval rating for the president, for example. We could be talking about a population of people that go to a museum, and maybe I want to take every fifth person and ask them what their favorite painting was in the museum. We're hoping that asking every fifth person might be representative of the entire group of people that went. That it's not some kind of weird artifact of just the sample that we ask for. So that's what I mean when we're talking about samples, trying to make a guess about what the population looks like. Okay. So let's see how this works using a very concrete example. And I have a population. Hold on a minute. I have a population in this bag. It's a population of blocks, of wooden blocks, okay? And these wooden blocks have numbers on them. And there's 25 blocks. And so I want to show you what the population looks like here, okay? And you can draw this if you would like. It's got 5 blocks in the center, and then 4, and then 3, and then 2, and then 1, okay? And it's symmetrical. And it is, in a way, a normal curve. We've talked about these boxes before, right? I could do a drawing like this around here and get my normal curve. These are the x values for each of the blocks. So there's one block with this value. There are 2 blocks with this value, and 3 blocks with this value, and so on and so forth. But I don't know what those x values are, okay? But given this distribution, I know that the mean, the distribution is right here, okay? It balances the deviations like we talked about before. This also happens to be the mode, the most frequent score. It also happens to be the median for this distribution since it is symmetrical. Okay, so this bag has these 25 blocks in it. And for inferential statistics, then, I want to try to make a guess about what the population looks like. And I'm going to tell you, you can assume that it's normal. But when I say, let's make a guess at what the population looks like, what I'm saying is, can we make guesses about the mean and the standard deviation? Okay? That's what I'm after. Excuse me, when I'm trying to make a guess about the population, I want to know what the average is. That's our gold standard descriptive statistics, like we've talked about before. But we're not going to be able to see the entire population. I happen to know it. I'm telling you this is what it looks like. You don't know what the values are. And so how are we going to make a guess for what the mu is, okay? And if we were in class, of course, I would say, let's make a guess. Guesses, make a guess, you guess. You know how I do that with you guys. Don't you miss it? And someone might say 500 for their guess. I'd be like, okay. And someone else might say 4 for the mean. And hopefully someone will say 36.72. And someone else might say 1,374. Without any other information, any of those guesses could be what the mean is. I mean, we don't have any information. I'm asking, what is the mean of this population? You say 56. Okay. You say 107. All right. I mean, I can't argue one way or the other in that regard. But let's get some information. And so what I'm going to do is I'm going to randomly sort of mix these up. I'm going to pull out now, in this case, one of the blocks, okay? I'm going to pull out one of the blocks, and it happens to have a number on it, and in this case, it's number 12, okay? So somewhere in here is the number 12. Has to be. I just picked it out, right? And these numbers are in sequence, so maybe this is 12. 12, 2 13s, 2 14s, and so on and so forth. Or maybe this is the 12. Or maybe this is the 12, or maybe this is the 12. We don't know. But I know 12 is in there somewhere. By the way, let's think about this for a little bit. I'm still going to ask you to think. If 12 is one of these numbers, I know that the mean can't be 107 because that would be too far away from 12 for that to make any sense. Okay? So we picked the number 12. And if you guys were in class, I would have someone pick that number. Now, what is your guess for the mean? Now, what is your guess? Because now we have some information, 12. And somebody might say, well, I think 12 is my guess for the mean. And I would say, awesome, because that would be my guess too if I didn't know any better. That would be my guess, 12. And then I would say, why did you say 12? The good wrong answer, remember those good wrong answers? The good wrong answer is, well, I picked 12 because I picked 12 for the value of the mean because that's the only information we have. And I'm like, oh, that's not that compelling, okay? It's true, but it's not a compelling argument. So let's untie this a little bit and think about when we mixed up all those blocks. I want to talk about probabilities, okay? What was the probability that we would pick this number? What's the probability that that would happen? Any guesses? Well, the probability would be 1 out of the 25 blocks, right? 1 out of 25. So the probability that I'm going to pick this block is, let's finish the math. 1 out of 25 is what? 4%, right? I mean, you can just do it on your calculator. So there's a 4% chance that I would pick that block out. I could go over here too and I'd say, well, there's 4% chance of picking that block as well. And in fact, there's a 4% chance of picking any individual block. Okay? 1 out of 25. There's 25 in the population. I'm picking out one block. So there's a 1 in 25 chance that I'm going to pick out a block with this value on it. Okay? Right here. But I want to go here to the mean. I mean, we know that this is the value for the mean, whatever that value is, right? And we have 1, 2, 3, 4, 5 blocks. 1, 2, 3, 4. 5 of the blocks in that bag have the value of the mean on it. So when I put my hand in the bag and pull out a block, what is the probability that I'm going to pick out a block with the value of the mean on it? What's the probability? Anybody know? There's 5 of those blocks, right? Out of 25 blocks total. So that ends up being the probability that I'm going to get a block with this value on it. And of course, if we do the calculations, this ends up being 20%. So there's a 20% chance that I'm going to pull out a block that has the value of the mean on it. All right? Because there's 5 of them. I mean, sometimes it makes it easier to talk about playing cards. Oh, and I miss playing my poker. About the worst thing you can do to spread germs is play poker at a casino. Anyway, the casino's closed, so I don't have to worry about it. And I wouldn't expose myself to that risk anyway. It's simple probabilities. So let me ask you this. What is the probability with a standard deck of cards? I'm shuffling them up. What's the probability that I'm going to randomly choose an ace? And of course, there are 4 aces in the deck out of 52 cards. So it's 4 out of 52. then I'm going to get an ace. Okay? So that's a little under 8%. You can do the calculation if you want. Every poker player knows that. Probability of a card of a certain value is about 8%. I could say, what is the probability of picking out the queen of spades? Well, there's only one of those out of 52. So that's a little under 2%. 1 divided by 52. And of course, when you're playing poker, that's the chance of getting a card, a single card, a specific card. Another thing I could ask is, what is the probability of getting any diamond? And of course, there's 13 diamonds out of 52 cards, which is 1 out of 4, because there's 4 suits. 13 out of 52, same as 1 out of 4, and that ends up being 25% chance. So this is how I'm getting my values here. There's one block with this score, and so I have a 4% chance of getting a block with that value. If I go here, there's 1, 2, 3, 4, 5 blocks with that value. So there's a 20% chance of getting a block with that value because there's 5 of them. Okay. Likewise, there's 2 blocks with this value. So getting a block with this value on it is now 2 out of 25, which ends up being 8%, twice the 4. A block with this value on it, there's 3 out of 25, so this is going to be 12%, 16%, 16%, 12, and 8. Those are it's a probability. I have a 20% chance of picking out the mean from that bag. I have a 8% chance of picking out the block with this value. I don't know what that value is. I have a 12% chance of picking out a block with this value. 8%, 16%. Okay? I hope everybody's okay with that. 25 blocks total. The reason this is 20% chance of picking out a block with this value. 12% chance of picking out a block with this value. Okay, and so on and so forth. So, when I put my hand in the bag and pull out a block, what's the best chance I have? What's the highest probability for the value on that block? Well, the highest chance is 20%. Okay? And so when I put in my hand, my best bet is that I picked out the mean. I have a 20% chance. Okay? Any other single value is less than that. But make sure you think about this logic here. Okay? My bet is I'm going to pick out the mean. That's my best bet. It doesn't mean that's what happened. It just means whatever I pick out, I'm going to use that as my guess for the mean because I have the highest probability of picking out the mean. Whatever I pull out, I'm going to guess that it's the mean. But this is inferential statistics, and we're going to have to get used to the chance that we made a big fat mistake. That doesn't mean I'm going to change my plans. I mean, I don't think it's going to be 90 degrees tomorrow. Could it be? I suppose, but that's just not a good bet. The probability is very low. Okay? And we talked about a meteor hitting the room, right? There's a possibility that would happen, but the probability is so low that I'm going to make the other bet. I'm going to say, I don't think a meteor is going to hit this room because that's the better bet. I could always lose. And this is the thing when we get into inferential statistics, and probabilities. It doesn't matter if you ultimately are correct. The biggest thing you want to do is make the best bet. You want to make the best bet. Now, there is a little bit of a quirk here. Some people will say, like, well, I'm going to say this is the mean. 12 is the mean because I had the highest probability of picking out 12. Hold on. Right? Did you catch the illogic there? No, you have the highest probability of picking out the mean, not the highest probability of picking out a 12. You have the highest probability of picking out the mean. This may be the mean. It may not be the mean. Okay? Let's pick out another one. I'm going to put this block back. We're going to stir these up. And this is actually gets pretty close to random. I mean, approximates random. Let's pull out another block. Let's see. Okay. That block is 15. Now, this is kind of weird because if we had pulled this block first, then my guess would have been that the mean was 15. The mean can't be both 15 and 12, right? We just picked out a 12. Now we pick out a 15. Herein lies the problem. Herein lies the problem with making guesses. Number one, we can always be wrong, okay? When we're making our guess, it's a probability statement, okay? And it can't be 15 and 12 at the same time. How do we get around this, okay? Well, most people are pretty comfortable with the notion that, like, maybe we should have more information. I mean, the political pollsters don't ask one person about their view of the president. They ask thousands, okay? Get some kind of an average. And just like we're trying to guess what's in this bag, boy, I wish I could take out more blocks, right? I know 15 is in there. I know 12 is in there. I know that the mean can't be both. The mean is one number. And so I made a mistake with 12, or I made a mistake with 15, or I made a mistake with both. And this gets frustrating sometimes. People are like, well, then how do we know what we're doing? Well, this is a problem that's not new to us. Maybe new to you, of course. But let's think about how we might be able to figure this out, to get a better guess. And that is, let's use a sample of more than one, okay? I mean, let's suppose that you were trying to figure out how good of a golfer I am, right? Hopefully I'll be golfing before too long. I hope some of you will as well. And I'd be like, maybe I'll, go golfing with somebody in the class, right? And I shoot a 105. Now that's not good, okay? Just in case you don't know, that's really not good, 105. And suppose I go golfing with Ryan and he comes back and tells the class, oh my God, Speck's talking about golfing all the time, but he sucks. He shot a 105, right? What does this have to do with populations and inferential statistics and samples? Well, so I have a certain golf ability, right? The population that we're talking about here is, how good of a golfer is Speck? Well, Ryan saw one round, and it was, what did I say, 105? Not good. And he says, Speck sucks, Speck sucks. That was like taking one block out of my golfing ability, right? Trying to assess my golf abilities, that bag of unknown. And Ryan saw one block. Now, I would concede to Ryan, well, if you've only seen one block, then that would be your best guess at how I golf, because same logic, He only saw me once, and I'm likely to play my average game. And he says, spec sucks. I'm like, wait, Ryan, wait, I'm not that bad. Oh my God, I can't believe it. I can't believe I shot a 107. It doesn't represent how I golf. Everybody getting it? Okay. It doesn't represent what's in this canvas bag of my golf abilities. You saw something that was weird. You saw something out here or out here. Okay. My average ability is much different than that. So Ryan might say, all right, dude, let's go golf again. And I'm like, okay, I'll pay because you got to, Now, if I golf again and I now shoot a 107 on top of my 105, Ryan's like, oh, okay, you really do suck. Like, no, that was not how I golf. Let's go again. And I golf again and I shoot a 104. Like, oh my God, 107. Well, all of a sudden, it's hard for me to argue, excuse me. It's hard for me to argue that my golf game is different than that. Let's think about another scenario. First game, I shoot a 105. I'm like, oh my God, Ryan, I just don't suck that bad. You got to believe me. You got to believe me. No, you don't have to believe me. Let's collect more data, right? And so we go out again. First round was a 105. Now I shoot a 94. It's like, Ryan's like, holy cow, huh? It's difficult to now reconcile that 104 in the first game, 105 in the first game and 94 in the second. Like, where is my average here, right? It's just like that 15 and 12 we just pulled out. I mean, it's like maybe 15 was the average and 12 was, aberrant, or maybe 12 was the average and 15 was, I don't know. I just don't know. Let's go again, right? So we play another round of golf. I shoot a 93. Then I shoot a 92. Then I shoot a 95. Well, in that case, the 105 seems to be an aberration, right? It was one of these extreme scores. But let's take a minute and think about that. If that was the only score I had, I'd use the same logic and say, I think that's the average of spec. Now that you have this other information, I need to sort of incorporate that and make an adjustment to my guess. Does that make sense? I mean, it's the same thing. I have students come to me sometimes. They're like, oh, Dr. Speck, I can't believe how bad I did on an exam. That's not, who I am. And what you're saying is that's not your average. That's not your population. That's not that canvas bag of your abilities. Okay. And I'll tell you something, and I'm being completely honest here. When a student says that, I'm like, yeah, okay. I mean, people have bad days. People have good days too, right? But what I'm hoping is when you take an exam that I'm tapping into the average somehow. But if you have a 61 on the first exam and an 85 on the second and an 87 on the third and an 84 on the fourth, that gives me more information. Like, that 61 was not representative, okay? Of course, you have to be careful, too, because it can work the other way, right? Somebody gets a 94 on the first exam and then gets a 61 on the second and a 58 on the third and a 70 on the fourth. I'm like, that 90 was probably not representative of your population, okay? So what we want to do is try to get the best sample to make a guess for our population mean. Now, I mean, the best sample, take all 25 scores. The best samples take all 25 scores. In this example, that means if we have the entire population, I don't need to make any guesses. I got the information. Short of that, when we only have a sample, it's like, I don't just want to take one block out. I want to take out 5 blocks. I want to take out 12 blocks. I want to take out 4 blocks. I want to take out 24 would be an awesome sample because that's almost everybody. Okay. Of course, if we're talking about political polling, 200 million people, that's not ever going to happen. I mean, the most we can do is maybe ask a couple of thousand, okay? Maybe 5,000. That's a tiny, teeny, tiny percentage of 200 million. But if it's representative, that's cool, all right? If we go back to Bob, remember Bob on Wednesday before we left? We said, Bob is weird, man. What do you have, a reaction time of 330 something when the average was 258? Remember that was we said, is Bob drunk? Does Bob have a closed head injury? The reason that we were wondering that is because if this is the average reaction time and Bob is that far away, something is weird, right? Now let's think about Bob. I'm like, Bob, are you drunk? Right? Bob's like, what are you talking about? I'm not drunk. I said, well, your reaction time is so weird. He's like, what? Oh, I wasn't paying attention, or I didn't know exactly what you wanted me to do. I'm not really that slow. Now here's the deal, folks. This is so important. I'm like, I don't know. I have no idea what Bob's canvas bag is with his population of reaction time. I know that he's got an average reaction time. What we saw when we had him at the computer was the reaction time was very slow. We're going to go back to this. I'm assuming that it was the most common for me to get Bob's average. I'm not saying it's the most common to get 337 or whatever it was. I'm saying it's the most common that I would get his average. It doesn't guarantee that I have his average. So we're going to do the same thing with Bob as we did with my golf game, right? Okay, Bob, you're not that slow. Let's do it again. Now, if Bob's reaction time is 333, 327, 346, 339, now I'm a lot more confident that I have a measure of Bob's slow reaction time, right? But if his first one's 331 or 333, whatever it was, if the first one is 333, and the second one is 260, and the third one is 249, and the fourth one is 273, I'm like, holy cow, that 333 was uncommon, unusual, weird for Bob. That Bob is really in here, but we happen to get a reaction time that wasn't representative of his population. Okay, there's all sorts of possibilities. If he gets 333, 335, 337, 340, 331, I'm like, Bob, you're slow. Now I'm really confident I can say that. If all of his scores are around the mean, except for that one that we had just done, then I need to reassess. I'm like, oh, I think that his mean is here, okay, or here. The point being, the larger the sample that you have, the more likely you're going to be in the representative of whatever population. I mean, if I have 10 reaction time tests of Bob, whatever the average is for those 10 is going to be my best guess. If you look at 8 golf games of mine, you're much more confident that you know what kind of golfer I am than if you just look at one. Okay, so we're going to develop that concept a little bit more. What concept? The more items I have from a population, the better I'm able to guess what that population looks like. Everybody with me? I'll repeat, right? I mean, this should be somewhat intuitive. The more items I have, the larger my sample, the better I'm able to guess at what's going on inside of that bag. Okay? The more golf games you see, the better you can guess at what kind of golfer I am. the more exams that I give you, the better I'm able to see. I mean, I never make a judgment of students based on one exam score. That is on how well they're doing academically. 2, at least. Let's do 3. Let's do 4. Okay. But you can't say that, oh, these bad test scores don't represent me if they happen 4 times. Or you can say that, of course, but it's hard for me to understand that. Likewise, though, you can't, I can't say, well, Johnny doesn't know this stuff, but he keeps getting 90s on the exam. That just doesn't make any sense, right? If you get 90 on one exam, I don't know whether you know the stuff or not, really. You could be lucky in the good way. You could be unlucky when you get a bad score, So I'm going to do some sampling to see how well you do. You can always do something weird, good or bad, but when things happen repeatedly, I get more confidence. All right, gives me more information. Okay, lots of sort of conceptual stuff, and as you now know, sometimes that's harder than the math. We're going to get to sort of the math version of this. We're going to get to the math version of this in the next lecture. But for right now, I'll show you what the mean for this distribution was. And here it is. The mean is, and the only, just to be clear, so it's my bag of blocks, and so I know what they look like. I'm sort of doing the reveal now, right? So the mean was actually 14. Okay, mean is 14. So there are 5 blocks. 5 blocks with the value of 14. Okay, 1 block with a value of 10. 2 blocks with a value of 11, and so on and so forth. 12, 13, 14, 15, okay, 16, 17, 17, 18, okay, and we can fill in the rest here. It's kind of nice because you could go back and replay this movie if you'd like. It might make sense now that we've done the reveal that there's 25 blocks in the bag. 5 of those blocks have the number 14 on them. So there was a 20% chance that I was going to pick out one of those at random. That didn't happen, but that's okay. We know that that's the highest percentage. If I were to put my dollar down here and say, okay, pick something out of the bag, and if you pick the number that I have my dollar in, I win the dollar, you would win most of the time if you put it at 14. You would win most of the time if you put it at 14. Okay? As it turns out, we picked out one of these 12s initially. We only had a 12% chance of that happening. Everybody with me? Those are different. It's 3 out of 25 is 12% chance, but it happens to be the number 12. I don't want people to get confused about that. We had a 4% chance of picking out a 10. No wonder that didn't happen because it's only a 4% chance. But it ain't 0, right? We had an 8% chance of picking out one of the 17s. If we go over to this 15, it's not surprising that we picked out a 15 because there's a 16% chance of picking that out. It's only second to the mean, okay, and so on and so forth. But from this chart, I hope, so if I put my hand in that bag again, let's do it. Let's see if you'll win $1. I'll pay you next semester. So here we go. Picked out a cube. Put your dollar on where you think what number you think I picked out. Put your dollar on what number you think I just picked. Okay? If you put your dollar here, why would you do that? There's only a 4% chance that I'm going to pick out that block. Okay? Somebody else puts their dollar here. Really? There's only 8% chance that this is a 17. There's only 8% chance. How about here? Put your dollar on the 13. There's only a 16% chance. Why would you not put your dollar here? Highest probability of winning. Okay? I'm going to put my dollar there. Let's do it. Well, that worked. But I honestly just did a random guess. I should end the movie right now because that's good. But I don't care if I win or lose. I don't care if I win or lose. I don't care if I win or lose. Did you guys hear that? I want to make a good bet. When I'm playing poker at the casino, doesn't matter if I win the hand. It matters if I made a good bet. And I talked to Professor Emmons in the math department. We play poker a lot. And we don't talk about whether we win or lose. We talk about whether that was a good bet, okay? Let's do this again because I just want to show you. This was not a fix, but it shows you how powerful. I don't have any in my hand. I don't have any. Here we go. Here we go. Here we go. Let's pick out another one. Okay. Oh, this is so good. Okay, I have a block. Okay, there it is. And let's see what number it is. Put your dollar on one of the numbers. 10 through 18, put your dollar on it, put your dollar on it, okay? Here we go, and here's the reveal, 15. Your best bet would have been 14. Second best bet was either 15 or 13, so, but it's still, why would you give yourself less of a probability, okay? And I'm so geeky, we can just do this, you know, I mean, it's like, so far we haven't seen an 11, a 17, an 18, or a 10. Why not? Because it's such a low probability. Here's another one. There's another 12. Okay. 12, okay. Not too crazy. You want to do, I know you want to do another one. See, this is not going to be so bad, is it? Oh, God. I feel sorry for you guys. I feel sorry for everybody. We're all in this crazy world. Stay safe though, okay? And maybe this will take your mind off of some other stuff. It's tough. It's tough. But let's try to get through it. Hopefully by June 1st, this will just be kind of a nightmarish memory. And I wish your parents well too. I hope they're doing all right. My buddy owns a restaurant in Pennsylvania, so that's closed. He's only doing takeout. Hopefully he can, make it work. Oh, there we go. There's a 17. Boy, I never would have bet on that. Never would have bet on it. Is it possible? Yeah, of course it's possible. Is it probable? No. Let's make a real distinction between probability, possibility. I think everything's possible, but we're going to make our decisions on probable, okay? Put my hand in, I'm probably going to pull out 14. Put my hand in, I'm probably not going to pull out an 18. Put my hand in, probably not going to pull out 11. Is it possible? Yeah, of course. These are all possible. We're going to talk about probabilities. So next video, we're going to take this distribution and we're going to see what happens when we take out bigger and bigger samples. Instead of just a sample of 1, we'll take out a sample of 2. And then we'll take out a sample of 4. And then we'll take out a sample of 8. Just like the golf, just like the grades, just like the reaction time. When I have more items in my sample, it's going to allow me to be more confident in my guess about a population I know nothing about. Remember, we started the video, I don't know what's in here, but we can still talk about the probabilities of things happening. The mean is the most probable, Okay, always, because it happens to be the mode. That's why. The mean is the most probable outcome, but there is some variability there. We'll see how the standard deviation plays out. Okay. Hey, you guys, try to not be stressed too much. I know that's not a button you can just turn off. I'm hoping you're well, and I'll see you in the next video. So be safe.